Welcome to Ask and Learn.
All right, so this one has 3 parts, and we are given an is equal to 3 times an minus 1 plus 2 to the power of n. And we want, for this part, to prove that an is equal to negative 2 to the n plus 1 is a solution to this. Okay, so note that an being equal to negative 2 to the n plus 1 implies that an minus 1 is going to be equal to negative 2 to the n minus 1 plus 1, which is equal to negative 2n. Okay, so then we note that 3 times an minus 1 plus 2n is going to be equal to 3 times negative 2n plus 2n is the same as negative 3 times 2n plus 2n, which is really like negative 3 plus 1 times 2n. So we're just kind of moving things around a bunch. So this is the same as negative 2 times 2 to the power of n, which is equal to negative 2 to the power of n plus 1, which is equal to an, right? Which is what we wanted to show. So we showed that this expression here, which is found on the right-hand side, is in fact equal to an when an is equal to negative 2 to the power of n plus 1. Okay, so check, that worked. Let's move on to part B. So part B has us looking at the roots characteristic equation here. So we're going to let an equal r and let an minus 1 be equal to 1. Okay, and so when we take our equation, which was an equals 3 an minus 1 plus 2 to the power of n, we're going to end up setting other functions of n equal to 0. So this 2 to the n becomes equal to 0. So when we put these values in, we just get r is equal to 3. Okay. And so note the solution of the recurrence relation then is going to be, and this is of the homogeneous one, so we'll get an, but this is our homogeneous part, will then be equal to alpha times 3 to the power of n. But we also need to consider the particular solution, because our full solution an is going to be equal to the homogeneous part plus the particular part, right? And in this case, the particular part is equal to -2 n plus 1. And so by their powers combined, we get that an is equal to alpha times 3 to the power of n minus 2 to the power of n plus 1. Okay, and so this was what we figured out in part A. And lastly, we are given an initial condition. A naught is equal to 4 and are to find the solution. Okay, so we're finding the solution from evaluating that an is equal to alpha times 3n minus 2 to the power of n plus 1 from part B. So we know a naught equals 4, so if a naught is equal to 4, and we put a 0 in here to our equation, we get that 4 is equal to alpha minus 2. Whoops, I'm sorry, I was reading the wrong problem. Here we have that a naught is equal to 1. Okay, so we get that 1 is equal to alpha minus 2. And so we can solve that. We end up with 3 is equal to alpha. So we just have to put the 3 in to our equation. And we end up with that an is equal to 3 times 3n minus 2n plus 1. But this can actually be simplified since that's the same number. So we really get an is equal to 3 to the power of n plus 1 minus 2 to the power of n plus 1. And that is the solution to this non-homogeneous linear recurrence relation.